Inverses are just when we flip the x and y. That's it. So, inverses with like fractions, it's when you flip the numerator and denominator. Well, with functions, we're talking about inverses of functions. It's when you flip the x and y. So a very basic example, if we had some f function and it was just coordinates, let's say like 1, 2, 4, -9, 3, 8. Okay. So we've got some function here. It's definitely a function, right? The x's don't repeat, 1, 4, and 3. I'll tell you, for an inverses, the y's can't repeat either. We'll define that here in a minute. But the y's don't repeat either. And can you shut that behind you, Jane? So an inverse function, you just flip the x and the y. So 2, 1, -9, 4, and 8, 3. Okay, very, very basic. Nothing too crazy, but a lot of, hold on one second, guys. There we go. A lot of different stuff kind of happens because of this, okay? A lot of different stuff happens because of this. We're going to talk about the graphs of this here in a minute. But let's go back to that fact that, look, whenever you flip the x and y and it becomes an inverse function, it's an inverse, really an inverse function. And this is how you notate it, okay? So an inverse function, you just make a little raised to the -1 there of x, okay? Now you're not raising anything to the -1. This is purely a notation symbol, okay? Purely a notation symbol. But when you do this, you cannot have y's that repeat either for the function. This is called one-to-one. Okay, functions must be one-to-one if they have an inverse. They must be one, because sometimes functions just don't have an inverse, okay? And that's okay, they just don't have inverses. And they don't have inverses when they're one-to-one. Now, one-to-one means we do not have any repeating x values, and we also don't have any repeating y values, okay? So this function here, f, is a one-to-one function because the x's do not repeat and the y's do not repeat, okay? And we'll dig a little bit into like graphs of one-to-one here in a minute, and then equations of one-to-one. But let's stick to these coordinates for now. So let's say we've got the g function, 0, 2, -1, 3, and 4, 5, okay? 0, 2, -1, 3, and 4, 5. Now look, this has an inverse because the x's don't repeat, so it's a function, right? The y's also don't repeat. So the inverse would be 2, 0, 3, -1, and 5, 4. But I want to graph this to kind of show you what's going on here. Good, got some different color markers. I'm going to graph the g function first. So 0, 2 is right there. -1, 3, right there. And 4, 5. 1, 2, 3, 4. 1, 2, 3, 4, 5. 4, 5 is up here. Whoop. Right there. So that's my g function. I'll leave it in that color, okay? And then I'm going to use a different color. I should use like a red or something. Hopefully this purple color looks a little different. So 2, 0. Now look, instead of a y-intercept here, 2, 0 is going to be an x-intercept. That's a little different. 3, -1. So 1, 2, 3, -1. And then 5, 4. So 1, 2, 3, 4, 5. And then we're going to go up 4 here. Okay. So notice here's these 3 coordinates. This is my inverse function. And here is my regular function. And what's neat about inverses is that they are always symmetric around the line y equals x. So that's the line right there, y equals x. Inverses will always be symmetric around. You see that, look, if I've made a fold on that line, it's not perfect, but it's pretty close. You'll see that like this coordinate would line up right here. And look, those are inverses, -1, 3, 3, -1. Look, they're symmetric around that y equals x line. Same thing with 0, 2, and 2, 0. They're symmetric around that line. And 4, 5, and 5, 4. Kind of neat, okay? So if you want to write that down, inverse functions are always symmetric around y equals x. We'll see that again too when we get to like equations. We'll see other inverses. Okay, so now look, we're going to make some theoretical kind of coordinate here, but I'm going to make up a coordinate. Actually, I'm going to ask you.
I have a quick question.
I'm listening. What's up?
So if it's not symmetrical, it doesn't work for the inverse.
Yeah, if you want to go that way, like if this wasn't symmetrical around, if these two weren't symmetrical, it wouldn't be an inverse. That's true.
Okay.
That's a vice versa type statement. Okay, so now I want you to think of adding a coordinate here that would make this function still a function, but it wouldn't have an inverse. Okay? So I'm going to ask you guys if you want to put it in the chat. What's a coordinate I could put here that keeps it a function, but it would not have an inverse? And just write it in chat if you think you've got a coordinate that would keep it a function, but just not an inverse function. Time to count down. 4, 3, 2, 1. Okay. 0, 2, 0. Well, yeah. Well, no, I'll tell you. 2, 0 would have been fine because you flip it. You got to think when you flip it, it becomes 0, 2. Look, you need to look at these y's. So 2, 3, 5. We can't repeat the y value for this coordinate for it to be 1 to 1. Okay? For it to have an inverse. So I'm going to repeat, like, if we repeated 2, we would just have to put some other number in here other than 0, -1, and 4. So let's say like 7. So if I gave you this function, 0, 2, -1, 3, 4, 5, and 7, 2, this function would not have an inverse. And it's because it is not 1 to 1. The y values repeat. That's okay. The y values repeat at 2. Okay. So now I'm going to get rid of that just because we already did this nice example from it. But I wanted to kind of give you an example. When you have a group of coordinates, what can make them not inversible, right? Still a function, just doesn't have an inverse. And the reason is it wouldn't pass the vertical line test. So if you want to know that, like when you flip it, think about this. When I flip these, this would become 2, 7. Well, now we don't have a function down here, right? The 2's repeat. So that's why we have to have 1 to 1. Look, if I flip these, the 2 becomes first and the 7 second. I've already got a 2, 0 there. So it would make it not a function. So kind of interesting. So when you're given a group of coordinates, how to tell if something's an inverse or not is just, or if it has an inverse, it's just 1 to 1 like that. Okay. Good. Let's go back. Yeah. So now let's get to like the equational side of these, and we'll come back to this part, the not repeating x's and y's and graphs here in a minute. But now we're going to kind of take a left-hand turn and really start where the book starts. I think the book starts in the wrong spot. That's why I go about it this way. So the book says, hey, if we, and this really relates to the last section. Okay, hold on. It turns out if you've got two functions, it turns out if two functions are inverses. So let's say we've got f and the inverse of f. When you take the inverse of them, and it does not matter the order, it always equals x. Okay, and the order doesn't matter. And if you do it one way, you'll get it the other, so you don't have to do it once. Okay, so when you take the inverses of functions, you always wind up with x, which is kind of neat. Actually, it's very neat. And the reason is it's because it's symmetric around that y equals x line. So if we look at a basic example, if I had like f of x, so this is really a good example from yesterday's work. F of x equals 3x plus 2. and g of x equals x minus 2. This is an example straight from your book, x minus 2 over 3. And the book says, show that each function is the inverse of the other function. So now look, if these are inverse, which it's already telling us they're inverses, we just have to take the composition. Now look, you can either put g into f or you can put f into g. I think it's going to be easier to put this f function into that g function. So I'm going to write it that way. Now, if I want to put f into g, that means my inside function is the f function. So g is going to come first. I'm going to do g composed of f. Okay, g composed of f. And what that means is I'm going to put f into g. And I wind up with 3x plus 2 minus 2 all over 3. And what will happen if they're inverses? Stuff will just start canceling. 2 minus 2 here is 0. 3 divided by 3 goes away, and it leaves me with x. Okay, so I have shown that these two functions are inverses because when I take their inverses, or when I take the compositions, I wind up with x. Okay, if you don't wind up with x, it means they're not inverses. It's not a big deal. Okay. Now I'll tell you on the test, I like asking this question, and what I do is I'll give you a third function, and I'll ask which two are inverses. Okay, so it'll be like f of x equals this, g of x equals that, and h of x equals, x minus 3 or something like that. And you've got to determine, just take the composition of two of them, and then if that doesn't work, do the other two, and then vice versa. So you have to just take the compositions until you find out which one is the inverse of the other. Okay, that's what I'm asking you for. Okay, no big deal. There we go. So next, your book goes over how to find inverses, which is actually kind of neat. So let's, and there's steps on page 303. I'll kind of just stick with those steps. Let's say we've got f of x equals, I'll kind of do a basic one. F of x equals, I'll do one that's not so basic. Let's say the cube root of x plus 4, okay? Now that plus 4 is not under the radical. It is outside of the radical. We can graph this one from transformations from a few seconds ago, right? But the cube root of x plus 4. So we're going to find the inverse, and I'm going to follow the steps on page 303. So step 1, it says replace f of x with y in the equation. So y equals the cube root of x plus 4, okay? That's step 1 from page 303. Step 2 says interchange x and y. So what that means is when you see a y, make it an x, and when you see an x, make it a y. So this becomes x equals the cube root of y plus 4. Okay, notice all I did was make the y's x's and the x's y's. That was step 2. Now step 3 says solve for y. If the equation does not define y as a function of x, the function f does not have an inverse function, and this procedure ends. If this function does define y as a function of x, the function f has an inverse function. Okay, so let's see what that means. Let's solve for y. Let's start there, okay? So if I want to solve for y here, I'm going to subtract 4. So I get x minus 4 equals the cube root of y, right? Then to get rid of the radical, I've got to cube both sides. Okay, so I'll wind up with x minus 4 cubed equals y. And now look, this is a function because you don't end up with a plus or minus. That's it, okay? I probably won't even do one. You're not going to see one on the test, and I'm not going to put any in the homework. So don't worry too much about that. But you wind up with y equals x minus 4 cubed. Now look, what you found is the inverse. So we're going to label it correctly. So remember, we started with f of x. So therefore, the inverse would be x minus 4 cubed. And now you can show this two different ways, really, if you want to check your answer. You can take the composition, or you could graph it. I'm going to graph it because it brings in something from that lecture that I had you guys watch a few days ago on 2.5, right? So let's do both of these when it comes to 2.5, section 2.5, as it pertains to section 2.5, I should say. Plus 4. Yeah. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So I'm going to graph F first. Now remember, if that plus 4 was on the outside of the radical or outside of the function, it meant that we went up 4 units. 1, 2, 3, 4. That what's the word? Transformed, but we shifted, vertical shift, right? We had a vertical shift to 4 units. The cube root looks like this, actually. The cube root function looks like that. Okay. It's not perfect, but it looks something like that. Now, look, I'm going to pause here for a minute, and we're going to talk about what 1-to-1 means. Remember, if I drew this graph and I asked you, hey, is this a function? You'd say, yeah, because it passes a vertical line test, right? Well, 1-to-1 has to pass vertical line and horizontal line test. And notice this goes up forever. I know it looks like it kind of comes back down, but this passes the vertical line test, and it also passes the horizontal line test. So for a function, this f of x to be 1-to-1, which means it's inversible, it has to pass the vertical line test and the horizontal line test, which this one does, okay? So that tells me it does have a function. So now let's graph the inverse. Okay, now remember, this is a -4 inside the function. So the -4 inside the function means we shifted to the right 4 units. Okay, and the cube function now, we're dealing with the cube function. So the cube function looks like this, something like that. It's not perfect, but it's something like that. Now notice these two graphs are symmetric around y equals x, right? Kind of cool. So these two graphs are symmetric around y equals x. That means that they are inverses. Remember, that's what you were asking me, Amanda, right? Hey, if they're symmetric, does that mean they're inverses? Yeah, it's a way to check it, okay? It's a neat way to check it. Now, just to do an example of what we did earlier, I am going to take the composition to show you that they're inverses as well. So this whole right-hand side of this paper is just me checking this, okay? So if I go over here, I think it might be easier to put the inverse into the original, okay? So I'm going to do f composed of the inverse. This is just to check it. So I'm going to take this whole function and put it in there for x. So we'd get the cube root of x minus 4 cubed, right? Because that's our new x. And then we got a plus 4 on the outside. Now notice this whole thing underneath here is cubed, and this is a cube root. They cancel each other out. So you wind up with x minus 4 plus 4 from the outside. The 4's cancel. You end up with x. Hey, this shows that it's an inverse as well. We kind of double checked it, right? It's symmetric around y equals x. And when you take the composition, you wind up with x. Pretty cool, okay? Pretty cool. Questions about that? Amanda, Brianna, do you guys have any questions about this? I'm going to do another example. I'm not leaving you hanging here. But do you guys have any questions before I get to this next example?
I'm good as of right now.
Okay. Well, let me give you an example, and I want you to try it on your own and see if you can get to the answer. And it's okay, of course, if you don't, because we're going to work it. Okay. Let me give you a linear function here. So f of x equals, let's see here. Let's say we've got 4x minus 3, okay? And I want you to find the inverses. You can use those steps on page 303. And I want you to find the inverse. Now also, actually, I want you to find the inverse, and then we'll graph it and check it, okay? Just in case it's wrong. Actually, no, I want you to check it. Make sure it's right. Make sure it's right. So find the inverse, and then check it to make sure it's right. I'll give you a few minutes. Nope. There we go. While you guys do that, I'm going to send an email out to everybody about no class tomorrow. Okay, let's see. So first I'm going to make that y. Then I'm going to switch x and y here. So x equals 4y minus 3. Then I'm going to solve for y. So add 3, and I get x plus 3 equals 4y. Then I'm going to divide everything by 4, right? So you wind up with y equals x plus 3 over 4. So f of x, and actually it's the inverse, right, equals x plus 3 over 4. Now, if you're going to graph this, we're going to have to break apart the 4 to make it the y equals mx plus b notation. So we could just take the inverse of each to show that it's, or not the inverse, I'm sorry, take the composition to show that it's the inverse. So I'm going to take f and I'm going to put it into the inverse. So I'm going to take, actually I'm going to do it like this. The inverse composed of f. So I'm going to take this and then put it into that x value. And I'd wind up with 4x minus 3 plus 3 all over 4. Oh yeah, these cancel and then the 4's cancel. And you wind up with x. So we definitely have an inverse. Now, just for fun, I'm going to graph this one. But to do that, I'm going to need to break this into y equals mx plus b. I've got to divide the 4 by both parts. So you're kind of unsimplifying that fraction a little. So this would be x over 4 plus 3/4. Now look, x over 4, I need a slope, I need a coefficient. So x over 4, or anything divided by 4 is the same as saying 1/4 times that plus 3/4. So that, I know it's kind of goofy to get to, but our inverse can be written two different ways, here or here, okay? Now I'm going to graph, so remember this is the original function. Here's the inverse. Let's see. Let's see how this looks. Okay, so we start with the minus 3 here, plus 4, 3. We go up 4. Okay. Okay. So I'm going to graph the original first. So down 3. 1, 2, 3. I'm going to go up. It's going to be really, really slope. I mean, a slope of 4 is really steep, right? So it's going to start at -3, and then it's going to go up 4. 1, 2, 3, 4 over 1, right? Because the slope's 4 over 1. And then 1, 2, 3, 4, and then over 1. So we're looking at something that looks like that, right? Okay, let's pull out the purple. Now look, this one has a fractional y-intercept 3/4. That's about right there, right? And then we're going to go up 1 and then over 4. 1, 2, 3, 4. So about right there. And notice these two functions are symmetric around, you guessed it, y equals x. Okay, so we've shown that they are inverses by taking the composition and by graphing. Now look, on the test, it's just going to say find the inverse. That's a way to check your answer. Okay, 2 different ways to check your answer that kind of brings both of them together. Pretty cool stuff. I know. You don't have to tell me. I do this for a living. Okay? Questions, comments, concerns. Okay. Oh, yeah. Your book then goes over like horizontal line tests, vertical line tests. I know we mentioned it, but look, let's just chat about it a little bit more than what I just did. Because these are the easy questions on the test. Okay, this is like the easy 4 points, 3 points. Let's look at a few graphs. Actually, let's look at a few graphs from 2.5. Remember, we had, actually, I'm going to make a few of these graphs. Okay, some of those parent functions from 2.5, we had the absolute value function. Remember, it was like a V, right? We had the square root function. It looks something like that. We had the quadratic function. It looks like that, okay? So for these, I'm just going to ask, hey, are these functions one-to-one? Which really means, do these functions have an inverse, okay? Now, if you look at this first one, to be one-to-one, you've got to pass the horizontal line test and the vertical line test. Wait, I did those backwards. Vertical line test and the horizontal line test. Notice that absolute value function does not pass a horizontal line test. If I drew an imaginary horizontal line, like right there, you'll see it crosses more than once. So I'm going to put under here, fails horizontal line test. Ham, lettuce, tomato, okay? Fails a horizontal line test. So therefore it is not one-to-one. Also, not inversible. I don't know if that's a word. But really not one-to-one is what we're worried about, but it means it's not inversible, okay? That second graph, though, look, it would pass a vertical line test. It would also pass a horizontal line test. So therefore, this is one-to-one, okay? It passes the horizontal line test. Now, the quadratic is a lot like the absolute value. It's going to fail as well, right? If I drew a horizontal line here, it's going to cross more than once. So therefore, it fails the vertical line or horizontal line test. It passes a vertical. So it's not one-to-one. Oh, yeah, that's just a fancy way to say one-to-one, shortcut way to say one-to-one, 1-1. Okay? Your book goes over that a little bit. I mean, I'm not too worried about it. It is on the test, and it's in the homework. But I'm not too worried about it. Okay? Questions about that, guys? Got like one other thing I need to go over in the section. Then we can do a good review for the test, which is great. Okay, the last part of this test that I really do like, and these are questions on page 309. I'll steal one from 309. How about that? I'll steal one. Number 36. We'll do an even. 36. So I'm going to make this kind of bigger here. 5. Okay. 5 and 3. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. Okay, so it tells us use the graph of f to draw the graph of its inverse function. So I'm going to graph what it gives us on number 36. Number 36, it starts at -3, 0, and then it goes up to -1, 2. Okay, and then it goes over to 5, 3. 1, 2, 3, 4. Wait, 1, 2, 3, 4, 5, 3. Like that. Now it keeps going after that. Shoots off. Okay. So that, and notice this is 1-to-1. It passes the vertical line test and it also passes the horizontal line test. Okay. So that's what it gives us. And it asks us to graph the inverse function. So all we have to do is really think of these coordinates, or really know the coordinate and flip it. So like this coordinate here is -3, 0. So that means the inverse to that coordinate would be 0, -3. So 0, -3 would be a y-intercept. 1, 2, 3. That would be 0, -3. Notice these are the inverses of each other, right? Now this next coordinate, -1, 2, the inverse of, -1, 2. The inverse of that would be 2, -1. So 2, -1 is about right there. Okay? 2, -1. So I'm going to connect those dots. Okay? And then 5, this was 5, 3. So we flip it, we get 3, and then 5. About right there. And it goes forever that way. And notice these two graphs, and I know I've drawn a lot on them, but kind of without all the coordinates written everywhere. Notice that these two graphs are pretty symmetric. It's not perfect because my digits aren't exactly the same across, but they're pretty symmetric around y = x. Kind of cool. Okay. So yeah, that's number 36. So it's going to give you a graph. Now you're going to have to determine the coordinates from the graph and then just flip them and then see that they'll be symmetric around y = x. Pretty neat stuff. Okay. Okay, let me give you homework and I'll ask if you have any questions. For homework, it starts on page 309. I want you to do 1 through 23. These are all going to be odd. And then 29 through 29 through 37. And that's it. We're going to keep it light. I really kind of, and I'm just focusing on what's going to be on the test. If we had another day like to, lecture, I would probably do a little more, but this is what's going to be on the test. Okay.